Hello there, my name is Dr. Farzad Newberry. I am going to be the principal instructor for this Introductory Biostatistics Distance Learning course. The format of the course will be as follows. We'll have 32 45-minute sessions, and although there will be a little bit of variability from time to time as different topics require, the general format that we're going to shoot for is to talk about a topic and then illustrate that topic using the statistical software package called Stata. So here is just kind of a brief outline of the course. I'm the instructor, Farzad, again. We'll be using Stata as the software, and although no textbooks are required, I've listed a couple of recommended texts here. One is The Principles of Biostatistics by Pagano and Gavreau, and then there's a really neat online textbook, which is also free. So free and online means you can access it anywhere, so that's good, called Open Intro Statistics. So those are references available should you need them. And as I already mentioned, we're going to have lecture topics followed by illustrations in Stata. So that's why you'll see these sessions are grouped in twos. We'll have a topic and then an illustration in Stata. So again, this is just meant to be in 32 sessions. We can just kind of cover the basics of biostatistics and things that people do pretty regularly. There's a lot here, so we'll try to move pretty quickly, but again, one of the nice advantages of a distance learning course is that if you didn't understand something or a topic was covered too quickly, you can always rewind and listen again. So hopefully that will be a nice benefit over the kind of customary coursework that we're used to, in which if you miss something, it's too bad because it's gone by. Here we can rewind and listen again. So hopefully that will help. I won't go through all these topics here right now because we'll go through them one by one in each session. But again, this will be a nice survey of introductory biostatistics. The meaning is not that at the end of this you'll be a biostatistician, but instead hopefully you'll be able to implement some of the simpler tests, and you'll be able to read papers from the literature and have a good understanding of them. Okay, so with that, and I should also take some time to say some thank yous to the University of Botswana Medical School, the Harvard School of Public Health, Drs. Rick Marlink and Dr. Mansour Farahani and others who have been instrumental in putting this together. So big thanks to them, and hopefully it'll be a helpful course. So why don't we get started? Okay, so I'm going to use this as my primary means of, there we go, of showing things during the course. Okay, so today we're going to talk about types of data. So types of data. We're going to talk about, sorry that's a bit messy, summary statistics. As well as some graphics. So those will be the topics for this first lecture. And just a bit about me, so you know who I am. I'm a biostatistician at the Massachusetts General Hospital, which is one of the teaching hospitals for Harvard Medical School, located in Boston, Massachusetts in the United States. My primary research focus is on HIV, tuberculosis, and other infectious diseases. So hopefully we'll try to use examples from HIV, but we might use other examples throughout the course as well. Okay, so overall in this course we're going to try to think about how we can think statistically, how we can choose the correct statistical analysis to apply, and we can focus on how to apply these concepts using statistical software, and we're going to be using Stata as I'd mentioned. And also when to seek help from a statistician because this is just an introduction. Okay, what we're not going to do is going to get into too many formulas. The formulas aren't that important. Instead, we're more interested in the concepts, and the software can do the computation for us. Okay, So again, biostatistics, like a lot of different disciplines, is one that continues to build on itself. So try to stay up with the topics, or because once you fall behind, it'll be tough to catch up. And again, we can always rewind and catch up that way. Okay. So let's begin. So what happens? We're in medical research, and people undertake research studies that involve careful planning prior to any data collection. And then once the data is collected, again, that's a very important part, the study design and thinking through that. But the focus for us is primarily going to be on data analysis. Sorry about that. So let's talk about a research study design. So what is involved in a research study? Research study. Well, we have one, the study design. What does that refer to? There we're talking about what is the experimental question. That is something we always return to in research. What is the question? So if you can lay out the question well, then you've completed the first step towards trying to conduct a proper study. Then we think about the sample selection. So what is the question? And then what is the sample? And that means, who are we going to collect for this study? Why are they appropriate? And who do they represent? Okay? So then 2 is data collection. So now that we've really thought out what we want to study and who we're going to recruit, then we're going to decide what should we collect. Obviously, if our study is about blood pressure, we're going to measure their blood pressure. We might measure factors that have been shown in the literature to be important predictors of blood pressure, such as age, gender, and so on. And then once we've done these 2 things, we've set up our study and we've collected the data, we then turn to number 3, which is the analysis. Analysis of data. So here we're trying to see, was there any effect? Did the treatment reduce people's blood pressures, or any other example that you can think of? And then we say, okay, so it seems like there was an effect in our study. Can we generalize this result? In other words, do we think that if this treatment were applied to everyone in the population, that the average blood pressure would go down, for example? Okay, so those are our 3 main steps in a research study. And you'll note that in each of these 3 steps, the study design, the data collection, and the analysis of the data, statistics are important in all 3. So in the study design, we have to define the outcome, the sources of variability, the analysis plan, the sample size, and so on. So obviously statistics involved there. In step 2, the data collection, we have to know what to collect. And in step 3, we do hypothesis testing, and then we think about generalizability or statistical inference in the 3rd step. So you can see, even though we start off with a medical question, all steps of trying to answer that medical question involve statistics. Okay, so let's move to a new sheet. All right, so one of the key, probably the most important concept in statistics is that of a population versus a sample. Population versus sample. Okay, and so I think everybody has an intuitive sense for what this means, but let's just be a little bit more clear. Okay, so sometimes we want to know something about maybe an entire country. I'll use the example of the United States because that's where I'm located. So we might be interested, again, using that same example about how a new treatment for reducing blood pressure might affect everybody in the United States. But unfortunately, we don't have the time or the resources to give everyone the treatment and then to see how everybody reacts to the treatment. So instead of giving it to everybody, we might instead choose a smaller sample of people to give the treatment and then see how they do, and then try to try to extend those results to the entire population. So in other words, if this is the huge population here, then we just collect a smaller part called the sample. And then we hope to make inferences from our sample to the population. Okay, so hopefully that concept is clear and one that everyone is familiar with. So in order to be able to take our results from here, the sample, and extend them out to here, the population, we want to make sure that our sample is representative and a random sample from the population. So that's where that first step, who are you going to collect? You want to make sure you collect a representative and random sample. Okay. So that's the population versus a sample, and we'll talk a lot more about that as the course goes on. Another key step is description versus inference. Okay, so let me go to a new page again. So description versus inference. Okay, so the first step in any study is to describe the data that have been collected. But again, we're not just interested in this small sample that we collected. Instead, we want to infer something about the larger population, what we talked about in the previous slide. Okay, so later in this course, we'll talk about how to do statistical inference. But again, the basic idea is that we collect a sample that we think is random and representative. We compute and describe that sample, and then we conduct statistical tests to extend those ideas to the entire population. Okay. Now let's talk about different types of variables. What are the things that we're going to collect in this study that we've designed? So variables. So in HIV kind of studies, I'm sure you're all familiar with the types of variables people sometimes collect. So they'll collect someone's age, their gender, their CD4 count, which is a measure of their immunological status, their viral load, and maybe something like their time to failure of first-line antiretroviral therapy, of ART, antiretroviral therapy. Oops, ART. Okay, so these are some of the examples of variables we might be interested in collecting. Now, it's useful to categorize these variables into different groups that they belong to. So let's go to a new page. So one example is a continuous variable. Continuous. These are sometimes called measured variables. And so what are some examples? Well, age, CD4 count. These are variables that can take any value in a long range. So again, age can go from 0 to whatever, 120. CD4 count can go from 0 to 1500 and so on. So these are continuous variables. Another type of variable is a binary variable. And what are some examples of these? Well, we can have male, female. We can have wild type of virus versus mutant, and so on. So these are just kind of yes, no. Sometimes people say success, failure, yes, no, just two groups. So that's what we mean here, two groups, binary variables. Okay? And then we can also have nominal, or sometimes they're called categorical variables, nominal or categorical. And these are just, as the name implies, different categories. Okay, so it's kind of thinking like having a binary variable, but with more than two groups. So what are some examples? We might say kind of race might be an example, or group membership. And so on. You can think of other types of examples. So continuous, binary, or nominal. And then moving along to a next slide, we can also have ordinal variables. And so ordinal variables are just like before where we saw with the categorical or nominal variables, but instead, these things, just as the name implies, have some ordering to the different categories. So one example would be the amount of pain that someone feels. We want them to categorize that, and they might say, well, is it mild pain? Is it moderate? Or is it severe? And so you can see that moderate pain is more than mild, and severe pain is more than moderate, and so on. And so there's a natural ordering to these groups. So this is what we call an ordinal variable. We might also have a count variable, and this will count the number of times something happened. So one example might be the number of lesions a patient develops. Okay, or the number of anything, the number of seizures, the number of anything else that you can think of. Okay, so that's an ordinal variable. That's a count variable. And the last one we're going to talk about here is a time to event variable. Time to event. And this might be time to death. So we give patients two different types of treatments. We measure the time to death in each of the two groups, and that's our outcome, a time to event variable. Okay, so that's a quick overview of the types of variables. We had continuous, binary, nominal or categorical, ordinal, count variables, and time to event variables. Okay, so those are our data types. Now, what are the different ways that we can express this data or summarize it in a way that can be helpful to us? Okay, so in other words, what is a way that we can envision the distribution of different variables? So what we're trying to describe is distributions of data. Okay, so we can do that numerically through summary statistics, which we'll talk about a little bit later today. Or we can do that through, so I'm sure you're used to the average, you've probably heard of the variance, and so on. We'll cover these in more detail in a little bit. Alternatively, we can use graphics, and I really, really recommend that you use graphics as much as possible when you're trying to learn about your data, because you know, the old cliche saying goes that a picture is worth 1,000 words. So if you can show these things graphically, it'll often really help you get some insight into what it is that you're after. Okay? So I'm going to just pause here, and then we'll pick it up right after. Okay, see you soon. Okay, we're back. Remember, we're talking now about ways to express our data and the distributions for different types of data. So now let's think again about how we might express a continuous variable using a plot. Okay, so remember examples of an example of a continuous variable we discussed was age. So one way we might do that is to look at a histogram, as I've shown here. Here's a histogram of age. And you can see how incredibly informative this plot is. It lets us know what the distribution looks like. Is it symmetric? Is it not symmetric? It looks pretty symmetric in this example. And also gives us an idea of the middle, or the central tendency as it's sometimes called, or you might be used to it being called the average, which is somewhere in here. And it also gives us a sense for the spread, or the variability. How far apart are the different ages of the people that we collected? So this is called a histogram, as it says on the top. It's a very informative way to summarize continuous data. And again, we'll look at how to produce these plots in Stata in the following session. Another example we could look at is a box plot. Again, this is another way to show the same data for a continuous variable. And here, this line represents the median, which we'll talk about a little bit more. And then these are the interquartile ranges, here and here. So the difference here represents the interquartile range. We'll talk more about this coming up, but I just wanted to show you the plots so that you have an idea of what's coming. Okay, so let's move to a new slide. And now that we've shown a few of the graphical summaries of data, let's think about a few of the numerical summaries. And so by far the thing that you're going to hear the most about is the mean. And in ordinary life, people call this the average. Or if you want to be very specific, this is the arithmetic mean, because there are other types of means, such as the geometric mean or the harmonic mean. But if someone just says mean, they mean the average or arithmetic mean. Okay? So to calculate this number, all we do is sum up the number of numbers we have and then divide by the total number of numbers. So this is easiest to see with an example. So suppose my data set is something really simple: 1, 3, 4, 5, and 7, for example. So in order to calculate the mean of these 5 numbers, so the formula is here. Let me write the formula. X bar is how we usually represent it, is equal to the sum from I equals 1 to n of xi divided by n. Now, don't get intimidated by the notation. This is just a fancy way of writing something very simple. So this big sigma, this is the Greek letter sigma here, this one, just means add. And this is saying from 1 to n. N is the total number of numbers we have. Here it's 5. 1, 2, 3, 4, 5. So it's saying add them up and then divide by the number there are. So here in this example, x1, x sub I, so x1 is 1, x2 is 3, and then plus 4, plus 5, plus 7. And it looks like we have 5 numbers total. So there. So 1 plus 3 is 4, plus 4 is 8, plus 5 is 13, plus 7 is 20. So this is 20 divided by 5, 5, which is 4. So the mean of this data set is 4. Okay? So all we did was add up the numbers we have and then divide by the total number of numbers there are. And remember, this is the notation that we have, and it's called x bar. Okay? It's not 2 bars, that's 1 bar, x bar. Okay, that is the mean, hopefully something that you're very familiar with. That is a measure of central tendency, okay? Now, we might also be interested in the amount of spread. Remember, now we talked about the mean. Going back to this picture here, the mean is here in this middle. Now we might want to describe the variability or the spread. So how do we do that? We do that with the standard deviation. Standard deviation. Okay, so hopefully you've all heard of that one as well before. And if you just square the standard deviation, you get back something called the variance. So these two concepts go together, the variance and the standard deviation. If you take the square root of the variance, you get the standard deviation. If you square the standard deviation, you get the variance. Okay, so how do we write that in our mathematical formulas? Remember, we're not going to cover too many mathematical formulas in this course. We'll usually rely on statistical software to do the computing for us, but where it's helpful to understanding concepts, such as this example, we'll take a look. Okay, so the formula for the variance is as follows. S squared equals, same as before, the sum from I equals 1 to n, but here's where something changes. X sub I, those are our data points, minus x bar, remember now that's the mean, squared, divided by n minus 1. Okay, and you might be wondering why it's n minus 1 instead of just n, but we won't get into the particulars of that here, but it's to produce an unbiased estimate of the variance, and we'll talk about what it means to be unbiased a little later. But this is the formula, and so that's the formula for variance. And now if we want the formula for the standard deviation, well, the standard deviation, which is s with no squared, is just the square root of s squared. So we can take this whole big formula we have up top, put a square root over it, and then we get our standard deviation. And we can calculate it the same way that we did the mean. But again, we're going to rely on statistical software to do that for us. Okay, so we won't do that here. Okay, so going back 3, 4, 5, 7. Okay, so our data set that we created was the numbers 1, 3, 4, 5, and 7. Okay, another way to measure central tendency, one way was the mean, and we came up with a mean of 4 before. Another way to get it is the median. So the median, which we can think of as the middle number or the 50th percentile. Okay, so to calculate the median, first we have to list all the numbers in increasing order, and then we find the middle. Well, here I've already listed them in increasing order, so I don't need to rearrange them. But in real life, you obviously, when you take the ages of people, you'll get them all mixed up. So we have to sort them and put them in order. And then, so here it looks like we have 5 numbers. So the middle number is here, it's 4. So in this example, both the mean and the median are equal to 4. So you might be wondering, well, why are we bothering with this at all? Instead, suppose our numbers are 1, 2, and 100. Okay? So the mean in this case would be 1 plus 2 plus 100, which is 103, divided by 3. Okay? Which is 34 and change, I guess. 34 point something or other. And then, but the median in this case would be 2, because 2 falls in the middle of these 3 numbers. Okay? So the median is sometimes preferred, like in this case here, where there's a large skew in the data. So, 34 doesn't really tell me that much about the center of these 3 numbers, whereas 2 tells me, okay, half of the numbers are less than 2 and the other half are greater than 2. So you can see when there's skew in the data, we might prefer the median as opposed to the mean. And so correspondingly, when we decide to work with the median instead, we also have measures of dispersion called the interquartile range. Interquartile range. And also just the range. Okay? So the interquartile range is the distance between the 25th and the 75th percentile. So remember, the median is the 50th percentile, as we'd mentioned. So the interquartile range is you find the number that's in the 75th percentile and also the number at the 25th percentile, and you take the difference between those two numbers. The range is just the distance between the minimum and the maximum number. Okay? So if we had those numbers 1, 3, 4, 5, and 7, the range here would be the largest one, which is 7, minus 1, or 6. Okay? So that is the range in this example. Okay. So we can, we're not spending too much time calculating these numbers because in real life we'll always be using statistical software to compute them for us, but it's nice when we're starting out just to get a sense of what they are. So, so let me show you what that looks like. We'll cover this more in the Stata tutorials, but just to give you a quick sense of what that might look like, we can do so in Stata in the next session. Okay. So let's talk a bit more about the graphical. Now that we've talked about the numerical displays a bit, let's talk again about the graphical displays. Okay. So here's our histogram. And we'd already mentioned that this gives us a measure not only of the central tendency, the central tendency, which is somewhere around here, but it also gives us a measure of the spread, which is how spread out are the ages that we've collected in this data set. Okay? So now if you look here, this looks pretty symmetric, the ages that we collected here, but we might also collect data and note a skewed distribution like we have here. And again, remember, when we have skewed distributions, these are times when we might prefer the median to the mean as a measure of central tendency. Okay? All right. So when we have a symmetric distribution, the mean and median are very similar, and they're very close to each other and they provide similar information. But if we have a skewed distribution, then the mean can be affected by high or low values more than the median. And we saw that in our example here, where we said the numbers that we had were 1, 2, and 100 here. And the mean turned out to be 34 and change, but the median was 2. So the mean was affected by this huge number 100, whereas the median was not. Okay? So general idea is use the median when you have a skewed distribution, and think about the mean when you have a symmetric distribution. Okay. Now, what's another way of summarizing a continuous set of data? We've talked about the histogram so far. We could also look at a box plot. And here's an example of a box plot. Okay? But again, a box plot now is for times when you're thinking about a skewed distribution and thinking about the medians and interquartile ranges and ranges, for example. So what do we mean by that? So if we go here, that line in the middle of the box is the median. Okay? So it looks like here in this example it's somewhere between 40 and 50. So our median is about 45, say. Then this upper boundary represents the 75th percentile. That means that 75% of the numbers in our data set are less than this number. That's the 75th percentile. And then this lower number is the 25th percentile. And now you'll remember, if we take the number that is represented at the 75th percentile and subtract the number in the 25th percentile, we get the interquartile range. So that is here. This is meant to represent subtracting the 75th percentile here from the 25th percentile, and that gives us the interquartile range. Then this final line at the very top represents the maximum, and the line at the very bottom represents the minimum. And if we subtract these two, take the maximum minus the minimum, we then arrive at the range. Okay, so when you have a skewed distribution, you want to think about the median, you want to think about the interquartile range, which is the 75th percentile minus the 25th, and then also the range, which is the maximum minus the minimum. Okay? All right. So that was for continuous variables, ways of summarizing continuous variables. We also said there were all sorts of other types of variables in addition to continuous variables. Another type that we mentioned was binary variables. Remember, this means they have two groups, male, female, yes, no, disease, no disease, and so on. These are also sometimes called dichotomous variables. Dichotomous just means that they have two categories. So how can we summarize binary or dichotomous variables? So the most common way to do this is to calculate a proportion. Okay, so suppose our variable is male versus female, and it turns out that we have, let's say, 4 men out of a total of 10 people in our sample. That means that 0.4 of the, or 40% of the sample is males, while 6 out of 10, or 60%, are females. Okay, so that's, here's a case where a graph wouldn't really give us much more information than the numerical summary. We have 40% males, 60% females. There's not really that much more to it than that. Okay. Next, we can describe nominal or categorical variables. Whoops. And remember, these include things that have more than 2 categories. So suppose eye color, for example. You can have brown eyes, you can have green eyes, you can have blue eyes, and so on. And so in the same way, we can talk about proportions. So if my variable is eye color, I might say that 7 out of 10 or 0.7 or 70% have brown eyes, and we have 2 out of 10 with green eyes, and then maybe 1 person with blue eyes. Okay, so again, summarizing this data, nominal or categorical variables, just like we did for binary or continuous variables, by representing the proportion. Okay, and we can do the exact same thing for an ordinal variable. Remember, an ordinal variable just has ordering, which was, we mentioned mild, moderate, or severe pain. There are similar categories like that you sometimes see in the medical literature. But again, we would categorize that using proportions. Okay? All right. Now, what about count variables? We had used the example of the number of lesions that a patient might develop. So here we can again just calculate the mean. Okay, so if it turns out that we have 5 people in our data set and let's say 2 people had 0 lesions, 0 lesions, one person had 1, one person had 2, and one person had 3, then the mean, which we represent by x bar, would just be 0 plus 0 plus 1 plus 2 plus 3 divided by the number of numbers there are, which is 5. And so here it would be 3 plus 6 divided by 5, which is also 1.2. So the mean number of lesions that patients developed here was 1.2. Okay. All right, so the last type of variable that we discussed was the time to event variable. So again, we might be interested in, we have a new treatment available and we want to see how that affects time to death for different patients. Okay, so a plot here again is very helpful. So let me show you a plot here. Here you can see it says percent survival. I'm not sure why this 150 is here because you can't have 150% survival, so that's not, I would delete that. It's not a good way to do it since 100% is the maximum. But again, now this shows you the different colors could represent different treatment groups, for example, and it could tell you the weeks until the event. The event could be death, it could be development of first-line resistance, it could be any event that you're interested in. And then it shows you the weeks until the event for the different treatment groups shown by the different colors. So again, here's a situation where a graphical summary is much more helpful than any numerical summary. But that's not to say that we can't compute helpful numerical summaries. If we wanted the median time to the event, well, that would just be at the 50th percentile, which would be here. Sorry, I missed it a little bit, but a line going across to the 50th percentile. Okay, and we'll talk about time to event variables very briefly at the very end of the course when we talk about survival analysis. Okay. So now these are just ways of summarizing different types of data that we've learned about. Okay. So sometimes we're interested in description and other times we're interested in comparison. So there's description versus comparison. Okay. So if you're just interested in description, which is often the case, you'll see in papers they'll have an estimate and a confidence interval. But then other times description is not enough, but we want to make a comparison. Okay, so maybe what is the mean survival time in the treated group versus the untreated group. So there we need a second variable, which we call an explanatory variable or predictor. So in my example, the explanatory variable or predictor was treatment groups. We wanted to compare time to event for the treated group versus the untreated group. Okay. So something we often see is something called a contingency table. Okay, and that's just a summary for the relationship between two dichotomous or binary variables. Okay, so let me just come up with an example. We might have males and females, and then we can have success or failure. So this is a way that I could summarize the relationship between two dichotomous variables. Just make a contingency table like this. Okay. Okay. So now, going back to continuous variables, we often hear about the correlation that exists between two continuous variables. Okay, so again, this is when we have two continuous variables and we want to describe the relationship or the correlation between them. Okay, so a positive correlation implies, so a positive correlation means that as one variable goes up, let's say variable 1, then the other variable goes up, variable 2. Okay? A negative correlation, on the other hand, means that as one variable goes up, the other variable goes down. Okay? So what are some examples? A positive correlation, we might have height and weight. So as your height goes up, your weight almost definitely goes up. So there's a positive correlation between height and weight. A negative correlation means that one is going up, the other is going down. So one example might be age and hearing. So as your age goes up, your hearing is likely to go down. So that's a negative correlation. Okay, so let's look at a picture to get a better sense of what we mean by this. Okay, so you can see in this first box here is a positive correlation because one variable on the x-axis is going up and the other variable is also going up. I'm looking here at the one in the upper left-hand corner, a positive correlation. Similarly, we might have a negative correlation. That means as one variable is going up on the x-axis, the other variable is going down on the y-axis. We might also have no correlation or really no relationship between the two, and that's shown here. Or the last one is a little bit more tricky because you can see there's definitely a relationship, right? There's this U-shaped curve, which is here. There's definitely a relationship between these two variables, but here it says no relationship. Why is that? Because a correlation measures a linear relationship. Here, this is a quadratic relationship shown in these data. So it's not a line, obviously, it's a curve. So that's something important to keep in mind. Correlation measures the strength of a linear relationship. So just because there's no correlation doesn't mean there's no relationship between the variables. It just means that there's no linear relationship. In other words, no relationship that I can represent through the use of a line. So we have to think about more advanced things when we're dealing with nonlinear relationships. Okay? So some things to keep in mind when we're talking about correlation. One is something you'll hear about often. Let me put it in quotes because you hear it so often, which is correlation does not equal causation. So what does this mean? It just means that when we measure correlation between two variables, it tells us whether there's a linear relationship or not. It is not telling us that changes in one variable are causing changes in another variable. So they're just measures of association. It's a measure of association, not of causation. Okay? So that's an important thing to keep in mind. Okay, so I think that's good for the first lecture. Next time we'll use stata to illustrate a lot of these topics that we talked about, and then in the next session we'll move on to probability. Okay, see you then.